How microchips are made. CPU manufacturing steps. Explained. Look around you, your phone, your laptop, even the car you drive, all depend on microchips. Inside a smartphone are over 60 chips with nearly 90 billion transistors, each smaller than a virus yet powerful enough to run AI and modern software. So how are these tiny circuits made? How do engineers transform sand into silicon, then into processors smaller than your fingernail? The journey takes place in semiconductor fabs, massive, ultra-clean facilities where wafers undergo nearly 1,000 steps over 3 months to become finished CPUs. Today we'll break down that process from silicon wafers to transistors, photolithography, and testing to see how the brain of modern technology is born. What's inside a CPU? A CPU, or central processing unit, is essentially billions of transistors connected by microscopic wiring. A modern processor may have 24 cores, memory controllers, and graphics engines, all packed onto a die the size of a stamp. One small circuit can hold 44,000 transistors, while the full chip contains over 26 billion. At the base are FinFET transistors, tiny 3D switches just nanometers wide. Above them sit 17 copper layers known as interconnects, acting like highways for signals. Local interconnects handle signals within circuits, while global ones connect the entire processor. For perspective, a single transistor is 36 nanometers long. Millions could fit across the width of a single human hair. The clean room, where chips are born. Chips are made in clean rooms, facilities cleaner than surgical theaters, covering areas the size of multiple football fields. Workers wear full-body suits not for themselves, but to protect wafers. A single dust particle can destroy thousands of transistors. Here, wafers move in sealed pods called FOUPs, delivered by robotic arms between hundreds of machines. Over 3 months, each wafer passes through nearly 1,000 steps before holding hundreds of CPUs. The scale is staggering. One fab can process over 50,000 wafers monthly, millions of chips. Precision is everything. Even the slightest error at nanometer scales can ruin an entire wafer. Baking the world's most complicated cake. Making a chip is like baking an 80-layer cake with 940 precise steps. If one ingredient or timing is wrong, the result fails. Chips are built layer by layer. Insulation, photoresist coating, UV patterning, etching, and deposition. Repeat this dozens of times and you get a 3D circuit. The value is extraordinary. A blank silicon wafer costs about $100. Once filled with CPUs, it can exceed $100,000 in value, making it more precious than gold by weight. The 6 categories of chip-making tools. To keep things simple, the thousands of steps in chip making can be grouped into 6 categories. Making the mask layer, creating nanoscopic stencils that define where material stays or is removed. Adding material, deposition, laying down metals, oxides, or silicon. Removing material, etching and planarization, carving or polishing layers to create structures. Modifying material, ion implantation. Firing atoms into silicon to form transistor regions. Cleaning, washing away contaminants with ultra-pure water. Inspecting, checking for defects using microscopes and sensors. Let's go deeper into each category, because this is where the magic really happens. Photolithography, writing with light, shortened. One of the most crucial steps in chip making is photolithography, writing circuit patterns onto silicon with light. First, the wafer is coated with a light-sensitive chemical called photoresist. A scanner then shines ultraviolet light through a photomask, which holds the design for that layer of the circuit. Wherever light hits, the photoresist changes, creating a stencil just nanometers wide. Etching or deposition then builds the structures in those exposed areas. Each layer of the chip requires its own photomask, and a modern CPU may use up to 80 of them, each costing hundreds of thousands of dollars. At scale, this makes semiconductor fabrication one of the most expensive manufacturing processes on Earth. The latest extreme ultraviolet, EUV machines, built only by ASML in the Netherlands, use light with a wavelength of just 13.5 nanometers. Each one costs over $150 million and is considered among the most complex machines ever created. Without them, today's 5 nanometer and 3 nanometer chips wouldn't exist. Deposition, adding material atom by atom. Once the pattern is made, it's time to add materials. Deposition tools essentially spray paint the wafer at an atomic scale. Depending on the step, engineers might add metals like copper or tantalum for wiring, oxides for insulation, silicon for building transistor structures. These tools use different physics methods, from chemical vapor deposition, CVD, to atomic layer deposition, ALD, to lay down films just a few atoms thick. Imagine trying to cover a football field evenly with a layer only 3 atoms tall. That's the level of control required here. Etching and planarization, sculpting the circuit. If deposition adds material, etching removes it. Etching machines use plasma or chemicals to carve away exposed regions defined by the photomask. This is how channels, vias, and wiring paths are created. After deposition and etching, the wafer's surface becomes uneven. That's where chemical-mechanical planarization, CMP, comes in. This process grinds and polishes the wafer flat again, ensuring each new layer starts perfectly smooth. CMP is repeated dozens of times to keep the structure precise across all 80 layers. Ion implantation. Engineering transistors. At the heart of every chip are transistors. To build them, silicon must be doped with impurities like boron or phosphorus to create P-type and N-type regions. Ion implanters fire beams of ions at the wafer, embedding them into the silicon lattice. It's like shooting baseballs into a concrete wall until they stick. Afterward, an annealing step heats the wafer to repair damage and activate the dopants. This process turns plain silicon into the working transistors that switch billions of times per second in your CPU. Cleaning and inspection, guarding against dust. Throughout fabrication, wafers are constantly cleaned with ultra-pure water and dried with nitrogen. Even a single speck of dust can destroy millions of transistors. Inspection tools like scanning electron microscopes check each layer for defects, alignment errors, or contamination. With chips taking 3 months and nearly 1,000 steps to make, catching mistakes early is critical. From wafers to chips, testing and packaging. After months of processing, a finished wafer holds hundreds of CPU dies. But not all are perfect. Some may have defects from dust, mask errors, or random variation. That's where testing and binning come in. Each CPU is tested. If it works fully, it may be sold as a high-end model, like an Intel i9. If only part works, it may be sold as an i7, i5, or i3. This ensures manufacturers don't waste partially functional chips. The wafer is then sliced with lasers into individual dies, mounted onto packaging with connectors, given a heat spreader, and tested again. Finally, the chip is boxed and shipped, ready to power your computer. From sand to silicon. Before all of this, though, we need the starting material, silicon wafers. It all begins with quartz sand, which is refined into pure silicon. This is melted and grown into a monocrystalline ingot using the Czochralski process, essentially pulling a giant cylinder of silicon from molten material. The ingot is sliced into wafers just 0.75 millimeters thick, polished to atomic smoothness, and marked with notches to align the crystal lattice. Each blank wafer costs about $100, but once processed, it can hold over $100,000 worth of CPUs. Why microchips are so hard to make? Making microchips is arguably the most advanced manufacturing process humanity has ever mastered. Consider this. The structures are smaller than viruses. The alignment between 80 layers must be precise within atoms. A single EUV machine has over 100,000 parts and takes 40 freight containers to deliver. Building a modern fab costs over $20 billion and requires thousands of engineers. Yet despite the difficulty, the result is astonishing. Billions of transistors working together to bring intelligence to our devices. The miracle of modern chips. Every time you tap your phone or open a laptop, you're using a device born from sand, refined into silicon, and sculpted atom by atom in ultra-clean factories. Microchips are the real engines of our digital world, powering everything from artificial intelligence to space exploration. And this is only the start. As we push toward 2-nanometer transistors, 3D stacking, and quantum chips, the process will become even more advanced and more vital to modern life. So what do you think? Are microchips humanity's greatest invention? Could we even live a day without them? Share your thoughts in the comments. And if you enjoyed this deep dive into the world of semiconductor manufacturing, don't forget to like, subscribe, and ring the bell for more explorations into the tech shaping our future.